Okay, we are now going to define another subspace that's associated with homomorphisms. And we're going to build off of what we just talked about, namely that when you have a linear mapping, say we call it H from V to W, then every element of W has a set of elements in H, in V that map to it. So this is H inverse of W. Okay. And that's true for any W here. Now the single vector here is not a vector space. There's only one single vector that is a vector space, which is 0. And it turns out that the inverse image of 0 has special properties. In fact, the inverse image of 0 is a subspace. And we'll see that. The proof will be shortly. Okay. All right, so let's consider this element H inverse of 0. Lemma. For any homomorphism, the inverse image of a subspace of the range is a subspace of the domain. In particular, the inverse image of the trivial space of the range is a subspace of the domain. The trivial space is the space that includes just the 0 vector. All right. And we're going to do this same closure argument that we've seen similar copies of before. Let H be a homomorphism from V to W. Let S be a subspace of the range space of H. All right, so consider the inverse image of S. So let's try to draw a picture here. Here we have V, here we have W, here we have H, and we have some subspace of W here. So let's see. Now, I want to consider the inverse image of S, which is going to be something back here. Not sure what it is. I'll just draw some irregularly shaped thing here. That's H inverse of S. Now remember, each element of S may have several elements of H inverse of S. Okay. Now, in particular, if I have 0 here, then 0 must be in the inverse image of S, because 0 of the H of this 0 must be equal to this 0. It's always true by linear property that a linear map operating on 0 always gives 0. Okay? So in particular, H inverse is not empty. So we need to show that H inverse is closed under linear combination. How do you do that? Well, you take any two elements in H inverse and show that the linear combination of those two elements is also an H inverse. Very familiar argument. Let V1 and V2 be two elements in H inverse of S. Take the linear combination, and we want to show that that's also in H inverse of S. Well, if I take H of this linear combination, I'm going to get a linear combination of the H's, okay, which is also a member of S, okay, because S itself is a subspace. Okay. So what does that mean? That means that the linear combination of these vectors also maps to an element of S. So this linear combination, in fact, is in the inverse image of S. Okay. This result complements lemma 2.1, that for any subspace of the domain, its image is a subspace of the range. So you can actually go backwards and forwards. Subspaces map to subspaces and vice versa. Now, the null space or kernel of a linear map is the inverse image of 0 in the range. Okay. Now we just got finished showing that in fact this is a vector space because 0 is a vector space. Okay. And you write that as script n of this linear map H. Okay. The dimension of the null space is called the map's nullity. Okay. So we have the rank of a homomorphism. We also have the nullity of a homomorphism. Okay. Now strictly, the trivial subspace of the codomain is not 0W, it's the set 0W. So we may think to write the null space of H inverse of this set. Okay, but we've defined the two sets, H inverse of W and H inverse of the set W, to be equal, and the first is easier to write. Okay, so we typically write H inverse of 0. Okay. Let's do an example of a nullity. Okay, think about the derivative map from the second degree polynomials to the first degree polynomials. The nullity of this map is going to be the set of second degree polynomials that maps to 0. Okay? The mapping will take this second degree polynomial to its derivative. So I need to map, I need to find out the set of all polynomials here that map to 0. Well, which polynomials map to 0? Well, a can't be 0 because 2ax is not 0 if a is not 0. B can't be 0 because I have a b over here. But c can be 0. If c is 0, no matter what c is, I will map this polynomial to 0. Okay, so I can summarize that. The nullity of d dx is the set of all polynomials for which the x squared coefficient is 0, the x coefficient is 0, but the constant coefficient is arbitrary. Okay, so it's actually the set of all constant polynomials, which expresses the fact that we know that the derivative of any constant is equal to 0. Now, according to the lemma, we know that this would have to be a subspace, and it is. The set of all constant polynomials is a subspace of the set of all rank 2 polynomials. Here's another example. If I take a two-dimensional vector and I map it to this linear combination of the components, you can work out that the null space of this mapping will be the set of all two-dimensional vectors such that 2a plus b is equal to 0. And here you can solve for a in terms of b. So we can parameterize this subspace as minus b over 2b. I can think of that as a line. This is a line with actually slope minus 2, so it would be something like that. It's b times minus 1/2 and 1. I could actually write that as b times minus 1, 2. It's the same thing if I just change the definition of the constant. So you can see that this is in fact a subspace of R2. Again, illustrating that the null space of a linear map is a linear subspace. Okay. Here's another example. If I take this mapping from the two-dimensional 2x2 matrices to the two-dimensional vectors, you find the null space is simply the set of matrices that map to 0. And you can solve this and get the explicit form of the matrix that maps to 0. Okay. The dimension of this null space is 2 because it's specified by 2 independent parameters. Now here's another one. You can read this. The dilation function, just multiply all vectors by a constant. It has a trivial null space because the only vector that maps to 0 is 0. Okay. The important theorem, a linear map's rank plus its nullity is equal to the dimension of its domain. So rank plus nullity equals dimension of the domain. The idea is that if you have nullity, that means the map loses some information. The rank gives you the dimension of the remaining information. So this is like saying the information you lose plus the information that you retain is equal to the information that you had at the beginning. Okay? That's kind of a loose way of expressing it, but it's sort of the idea behind this theorem. Okay? Now here's the proof. Let H from V to W be a linear map. Let B1 through BK be a basis for the null space. Okay, so that means that K is equal to the nullity. Okay. Now I can expand this to a basis for the entire domain. We already know that we can do that. We can expand any linearly independent set to be a basis of the entire vector space. Okay. We will then show that the h of the vectors that we added gives a basis for the range space. All right. So here I have n is equal to the dimensional domain. And if we can show that these vectors, how many vectors are there here? There's actually n minus k vectors. If we can show the range space has a basis of n minus k vectors, that means that the dimension of the range space is equal to n minus k. And we're getting k plus n minus k is equal to n. So this entire proof hinges on the proof that, in fact, this set of vectors here, h of bk plus 1, all the way up to h of beta n, is a basis for the range space. Let's see how we can prove that. To see that this basis here is linearly independent, let's consider the possibility that these vectors sum to have a non-trivial linear relation that sums to 0. Okay, so let's try to see what this implies. If we can show this implies that all of the c's are equal to 0, then we're good. Okay. All right, so suppose we do have that all these vectors add to 0. Okay. We can use the linearity property to say that that means that h of this linear combination of the betas must also be 0. Okay. And that means that this vector, which is a linear combination of these basis vectors, must be in the null space. But we already know that this is the basis of the null space over here. Okay, so any linear combination of these vectors can't be in the null space, or that would mean that these vectors are linearly dependent on these vectors. Okay. So the only possible way for this linear combination of these vectors to be in the null space is for the sum of these vectors to be equal to 0. Okay. So, and the upshot is, if I have a linear combination of these vectors here, h of beta 1 through h of beta n, that gives me 0, in fact, it must be the trivial linear combination. Okay. And these vectors are linearly independent. Okay. To show that BR spans the range space, consider a member of the range space h of v. Express v as a linear combination of the members in BV. Okay. So I can write h as h of this linear combination because I know that b1 through bn forms a basis of the entire domain. Okay. So take this linear combination, use the linearity property to write this as a linear combination of h of the basis vectors. But these guys are all in the null space, so these guys all go to 0. Okay. So h of v can be expressed as a linear combination of h of beta k plus 1 up to h of beta n. That's true of any vector in the range space. That means that these vectors, h of beta k plus 1 up to h of beta n, must span the range. Okay. So the upshot is h of beta k plus 1 plus ... up to h of beta n is a set of linearly independent vectors that also spans the range space. It must be a basis of the range space. The range space has dimension n plus 1. The null space has dimension k. The domain has dimension n. And we have the result that the domain dimension equals n is equal to the null space dimension, which is k, plus the range dimension, which is n minus k. Okay, so that gives us the proof. Here's an example. If we take the projection from R3 to R2, projecting to the xy plane, all right, the null space is simply the z-axis. You can verify that the z-axis collapses down to 0. Okay. So its nullity is 1. Okay, the null space has dimension 1. And you can see, obviously, the range space has dimension 2. And that gives us 1 plus 2 equals 3, which is the dimension of the original domain. Okay. Right. Now, the action of the projection is that the third dimension collapses. A linear combination of in the domain C1E1 plus C2E2 plus C3E3 is sent to C1E1 plus C2E2 plus 0. Okay? All right. So basically, this sitting above every point in the xy plane is something that looks like a copy of the null space. The null space is here, but the inverse image of any point here in the plane is not a vector space itself, but in some sense it's like a translated copy of this null space. Now, when you do abstract algebra, you'll find out that there's a technical term for this, which is called coset. This inverse image of a non-zero entry, non-zero vector in the plane is not a vector space in itself, but it's a coset. It's kind of a copy. It looks identical, but it doesn't contain the zero element. Let's look at another example. If we take the derivative function and the range space, if the derivative function is acting on on quadratic polynomials, the range space is linear polynomials. So the range space has dimension 2. And we already saw that the null space was the set of constant polynomials. So the null space has dimension 1. So again, we have 1 plus 2 equals 3, which is the dimension of P2. Another example, suppose we take h, the function from R2 to R1, given by this algebraic relationship. We computed before that the null space was this line in R2, which is one-dimensional. You can see also that the range is one-dimensional. The original vector space is two-dimensional. 2 equals 1 plus 1. This verifies the relationship. Okay. Here's another example. Here in the null space has dimension 0. The range space has dimension 1, dimension 2. The domain has dimension 2. So we have 2 equals 0 plus 2. This also verifies the same relationship. Okay. This verifies the same relationship. So I won't do this explicitly. Right. Another lemma, under a linear map, the image of a linearly dependent set is linearly dependent. Okay. And this proof has the same flavor as all of these proofs that we have. Let's take a linearly dependent set and show that it maps linearly to another linearly dependent set. Okay, so suppose we have a linearly dependent set, means there is a linear relation that gives 0, where the CIs are not all 0. If I apply h to both sides, that gives me a linear combination of the images of each of the bases of the v vectors. Okay. We also know that if this linear combination of v's is 0, then h of that linear combination is also 0. This means that there must be the same coefficients can work to give a 0 linear combination of the h of v's. Okay, so the image of a linearly dependent set is linearly dependent, and since if it's not linearly dependent, it's linearly independent, we also have the image of a linearly independent set. Well, no, you can't say that. I'm sorry. You have to be careful about that. Okay. Here's the trace function. If we map the two-dimensional matrices to the real numbers, okay, we're just summing the diagonal elements. Here you can see the dimension of the range is 1. Okay. This set of matrices is dependent. Okay. Let's see. Yeah, these three matrices are dependent because I take 2 times the first plus 1 times the second minus the third. Okay. And these three vectors are the images under the trace map of these three matrices. Now, in fact, in R, any two numbers are linearly dependent. So I have this linearly dependent set that maps to a linearly dependent set. Now, this example also contradicts what I was about to say, that the linear map of image of a linearly independent set is linearly independent, if you just took these two matrices here, these two matrices are linearly independent, but you can verify that their images are not linearly independent. Okay, if V is an n-dimensional vector space, these are equivalent statements about linear map from V to W. If H is 1 to 1, then H has an inverse from its range to its domain that's a linear map. Okay, and this is from the range, not the codomain. Okay, the range in general is a subset of the codomain. We're not saying that V is onto, so it's possible that there's some elements in W that are not hit by this linear map. But if we take the range, the map H is restricted to the range, has an inverse. Okay. Now in this case, we can also show that the null space of H is 0. So that means the nullity of H is 0. That means the rank of H must be n. And if B1 through Bn is a basis of V, then H of B1 through H of Bn is a basis for the range. So first we show 1 is equivalent to 2. Then we show that 1 implies 3, implies 4, implies 5, implies 2. All right, so for 1 implies 2, suppose that the linear map H is 1 to 1, and therefore has an inverse from the range to the vector space. Again, well, you have to restrict it to the range. The linear map will be onto the range. The domain of that inverse is the range of the mapping, and thus a linear combination of two members of it has the form C1 H of V1 plus C2 H of V2. Okay, so if I take two elements of the range, I can write it this way. Okay. If I take H inverse on this combination, if I take H inverse of this linear combination, I can rearrange the function using linearity properties, and that gives me C1 V1 plus C2 V2, which is actually C1 times the inverse image of this element in the range plus C2 times the inverse image of this element in the range. So that means if the linear map has an inverse, the inverse must also be linear. Okay. This also gives the 2 implies 1 implication because the inverse itself must also be 1 to 1. Right. Okay, of the remaining implications, 1 implies 3 holds. Let's see what 1 implies 3 means. H is 1 to 1 implies that the nullity of H is 0. 1 implies 3 hold because any homomorphism maps 0V to 0W, but a 1-to-1 map sends at most one member of V to 0W. Okay. And 3 implies 4 is true since rank plus nullity equals the dimension of the domain. Okay. To show 4 implies 5, I'm going through this fairly quickly, but that's okay. It's important to get the result. For 4 implies 5, 4 is this one here, the rank of H is equal to n. And if B1 through Bn is a basis for V, then H of B1 through H of Bn is a basis for R of H. So the H maps a basis to a basis. Okay. All right, so given that B1 through Bn is a basis of the domain, we want to show that H of B1 through H of Bn is a basis for the range. We only need to show that it's a spanning set, because we know that the range has dimension n. Right. So consider H of V, which is in the range. I can express V as a linear combination of basis elements. And then using the linear property, I can get H of V as a linear combination of H of the basis elements. And that takes us to the end of this chapter. Not a moment too soon.